Okay, thank you very much. Thank you to the organizers for the invitation to talk today. I find it very interesting. So it's a different community from this workshop to the usually I attend. I find it very enriching. And yeah. So what I want to do today is what I want to talk about, what the title says, but I also somehow added some, I guess, personal review of certain things that I think relevant for this workshop, and somehow, and I think some of you may have heard these things before, but I think yeah, it's sometimes good to repeat certain things. I believe. So yeah, so everything that I want to say has to do with spatial infinity. So and then in particular, what I'm really interested and been interested for a long time is the relation, so the asymptotic behavior of the relational field at both null infinity and spatial infinity, and then how these two behaviors somehow come together. So this sometimes is called the problem of spatial infinity. I also want to, there's another message somehow, which I think probably Leonard Kerberger last week probably also emphasized this quite a lot, right? So there is all this framework going back to the 60s by Penrose on describing isolated systems using conformal compactifications. This has been very influential. However, well, I think now everybody agrees, or at least say in mathematical relativity, people agree that well, it was very important, right? It's very restrictive. Nevertheless, somehow it gives important insights and has pushed the field forward. So this is another message. And then here, well, I want to sell my own particular approach to studying spatial infinity and asymptotics in GR, which is a certain framework by Helmut Friedrich based on so-called conformal field equations, which allow to relate quantities at spatial infinity on a Cauchy surface at null infinity. Right? And then this allows us to do like very detailed analysis of how radiative properties relate to properties of the initial data. And so as an example, I want to show how you can make use of this framework to the computation of asymptotic charges, so these BMS charges in general relativity. Okay, so then this is my brief introduction, right? And then I somehow could not avoid giving this quote by Jos Stewart in a very nice book of advanced relativity. So there is a chapter of asymptotics of the gravitational field, probably on the early 90s, and then, well, then he was writing to make the reference to Czechoslovakia, saying that this is asymptotia is a faraway land of which we know little. So I think the situation has improved a bit, but I think there are still things that we don't know or we don't control fully, right? Let's say. And not to say that because of that, so you can imagine, so there is a vast literature on the asymptotic gravitational field, so spanning 40 years plus, right, with a lot of ideas that come about, then die, then sometimes they are recycled, then people try other things and so on. So it's really hard to keep track of this. But I guess it's fair to say that a lot of it really builds on Penrose's idea of asymptotic simplicity. Some way or the other is influenced by it. And I guess for someone coming from mathematical relativity and say Cauchy problem and so on, most of it is somehow formal in the sense that there are a lot of numbers, so there are people make number assumptions, some of them more or less justified on physics and so on, that may or may not be generic. And I think for mathematical relativists, I think the point really of the daily bread or the motivation is really to verify whether these assumptions are or not generic, right? So, okay. And then again, just to, so people have devoted many decades or big chunk of their lives trying to understand all these asymptotics or the assumptions around asymptotics. And well, and I just listing here some contributors. I mean, I think, well, certainly for me, the one that has been most influential is Helmut Friedrich, and then which I now take on somehow the formalism, but then certainly Piotr Kruschel, and then Bobby Weig, Bernd Schmidt also were pioneers of this. And then obviously there is another school somehow, which comes from somehow based on the work by Demetrius Christodoulou and Kleinerman on the stability of Minkowski, and then which now moves to stability of black holes, where, I mean, all these issues have become relevant. And then, well, there are other work by Kleinerman, Niccolo, Lindblad, Rodniansky, more recently, and I think this is very promising from my point of view, so there's a community made use of methods of microlocal analysis, and people, particular, so Peter Hinz and Andras Vashi, who have looked at asymptotics also from a slightly different perspective, and making use of from a different arsenal of mathematical methods and techniques. And then certainly also, well, I put here also Leonard, but well, I guess Leonard somehow belongs also here to this school, right? And then, I mean, obviously I don't want to be comprehensive, or it's not possible to be comprehensive here. And what I want to point out is that although people have made big progresses on this area in recent years, there is, I think, some key questions, right, that remain unsolved. I think more than unsolved is, I think people know what sort of theorem you would like to have, right? But then there are, at the time, somehow not the proofs. So there's a lot of work lying ahead, right? But I think the key ideas on somehow how things fit together is already fairly well understood, I would say. Okay, and so because of, well, just mentioned this, so I just quickly mentioned Penrose's definition of asymptotic simplicity, mostly because of historical reasons and because it has been highly influential on the field, as I have said. And so Penrose's idea really was the following, right? We want to study isolated systems. How you like to characterize those, or how would you characterize those? And then his idea was, okay, something that's an isolated system should admit some sort of compactification, which is similar to that of that you can do for Minkowski spacetime, right? And then this is really somehow at the core of this definition, which I would not read, right? But then the key idea, so the key point here is, and which has been the source of controversy for decades, is the requirement that this extension is to be smooth. Okay? And then there's also another somehow aspect to this definition, is that it really refers to null infinity, so the future null infinity and past null infinity, but never really says how these two components fit together, and moreover how they fit together with a spatial infinity, right? So then had been some work later on by Ashtekar, Hansen, so which had also been highly influential, right? Try to bridge the gap and bring these two things together, right? But then again, for that, then you have to make certain assumptions, right? So yeah. And well, I guess somehow you want to sell this, right? So then there is somehow an underlying idea, which I think is very powerful, is that what you want to do is to study asymptotics of the gravitational field, and you want to have a geometric framework to do this, right? So really, this is the point that is really at the core of all this business. Okay, and I guess, so why so much emphasis on this aspect of smoothness? Well, so the idea is that the smoothness at null infinity somehow is a way of encoding in smoothness in conformal world is encodes the decay of fields, say particularly so-called peeling theorem, right? And as a corollary, if somehow you don't have smoothness, right, or you have some restricted level of smoothness, this means that your fields will not satisfy the peeling behavior, right? So you will have some sort of modified decay. And just to make somehow, I mentioned this, this also has been something that is being very influential in the field. So we have the so-called peeling theorem, right? So then, so just quoting here, this in the form of theorem. So this is, you can trace it back to 65, right, by work by Penrose. Although, okay, some version of this also appears in the world of Bondi, Sachs, and Messner, and so on. Right, when the idea is you have a vacuum space-time with a vanishing cosmological constant, and so then there is an assumption here that space-time is asymptotically simple, so that you can obtain this conformal extension, which is smooth. If this is the case, then the component of the Weyl tensor respect to a certain frame, which is adapted to a certain foliation, right? But this adapted to the geometry of null infinity, then satisfy this hierarchy of decay, right? So where you have the fastest falling component, subside node, which goes like 1 over r to the fifth, and then you go increasing powers or somehow decreasing the powers up to down to the radiation field, psi 4, which is most slowest part of the field, right? Going like 1 over r. Okay? So, let me give this context, right, and these ideas of Penrose. So, well, I guess a couple of questions you would like to answer is what is how generic are spacetimes satisfying peeling or spacetimes which are asymptotically simple, and then how were you if you want to construct this explicitly, say with a computer or through a CRM, how you would proceed to do that, right? So I guess then the first one. So how large is a class of spacetimes which admit this compactification? There are some examples, explicit examples, right? So like Minkowski spacetime, but then you see that there are actually not that many besides Minkowski, right? So then there are other some solutions like say for example the symmetric, right? The particular exact solution, which have some sort of pathology. So actually, yeah. So there are not that many examples where you can apply all this framework, right? And then I'm just taking away black holes, right? So I'm not talking about those things. So let's say something that is like asymptotically Minkowskian. Basically, you only have Minkowski, right? And then, right? So then the question is, are these spacetimes, right, which are asymptotically simple, like just islands, say, on the space of solutions, or this like an open set, right? And then, as I said, how you specify the initial conditions, say, to the metric and extrinsic curvature, which will give you this asymptotically simple spacetime. What extra conditions would you actually require to ensure that you have the required global behavior? Okay. So now, this question is somehow difficult because there is a technical issue, right, which is already also described by Penrose. So it's actually quite remarkable how many of the key problems were already very quickly identified early in the field. And it's the following. So I think in one motto is that you have mass on your spacetime. So you have a Cauchy slice where the mass is non-zero, then there has to be a singularity of the conformal structure at the point at infinity, right? At spatial infinity, right? So how you see? So one way of thinking like this. So you have your Cauchy hypersurface, and then you have your spacetime, which plausibly will develop a scribe plus and scribe minus. So then there is some sort of time-like singularity that emanates from spatial infinity, which is a bit like this negative mass singularity in Schwarzschild. So Schwarzschild with negative mass, right? So this is one picture. Another way of thinking of this is you have your initial hypersurface, then the spacetime that is arising from this data is somehow everything that is outside the cone, so the complement of the cone, right? And then the singularity is inside cone and is somehow causally disconnected, right, from the interior of spacetime, but nevertheless, because somehow it starts really at the vertex of scribe, well, things could be propagating here. So then, from a technical point of view, so this causes a lot of problems, and then makes formulating an initial value problem for a setting like the one I have here, right, with a singularity, right, at this point, particularly complicated. Yes. Yes. Yes, right. So there is a suggestion here, right, that in fact, if you have you conformal your like manifold here, in fact, the manifold could be extended beyond, right? And then in fact, this is the way, actually, for example, in the theorem, the way the spacetimes are actually constructed, right? So what you do is you try to obtain a metric which is regular at the conformal boundary, so it actually doesn't see the conformal boundary, right? So you only know about the conformal boundary because you have this extra information given by the conformal factor, right? And then you know where the conformal factor exists. That, yeah, right. So this is a bit of a, it's more like a cartoon, right? But in fact, it's actually, yeah, one could think in this way, right? And then there are many spacetimes where you actually can do this construction explicitly. Say, well, for example, Schwarzschild or Rice-Nordstrom, Friedman, Rice-Nordstrom, where you can actually see this quite in a quite detailed way. Well, so the motivation is I guess a mathematical trick to be able to construct the solutions, right, through PD theory. So in fact, I will say something more about that in a couple of slides, right, and then hopefully this will be a bit more clear. So any other questions? Okay. Yeah, in fact, not more slides. So in fact, in this slide. Okay, so as I said, so this idea that if you want to formulate a Cauchy problem, right, where you do the data on a Cauchy hypersurface, is kind of problematic, right? If you want to do it in conformal world, because you have somehow the end of your slice with this singularity, right? So Helmut Friedrich had this idea of not starting off from a spatial infinity on an hyperboloid. So this is an hypersurface, which is space-like and which intersects spatial infinity, right? And then for example, well, so in Minkowski, so there are a lot of examples of these hyperboloids. So really are, say, in example of those are hypersurfaces which satisfy t squared minus r squared equals to some positive constant, right? So that will give you examples of these hyperboloids. And some of them actually in this picture look are horizontal lines. So somehow it's an artifact of the distortion implied by the conformal rescaling. And so then in Minkowski, so you can consider one of these hyperboloids, and you can see what does the data imply like this, and then you can use somehow sort of a perturbation of and use some perturbation methods, and then you can actually prove that perturbations, nonlinear perturbation of the data actually lead to a nonlinear solution, right, on the future domain of dependence of the hyperboloid, right? To say that by prescribing data which is close to data for Minkowski on the hyperboloid, you obtain a space-time to the future, right, which has the same global structure as Minkowski space-time, right? And in particular, so the generators of null infinity, so they actually meet for the perturbation thing meet at a point. So this point I plus, so you can prove this quite accurately. Okay, so now so just to answer your question, Ali, right? So let me just get very so the way this is proven, right, is that so it's well known that this Minkowski spacetime can be conformally embedded on this Einstein cylinder, right? So then you have the Einstein cylinder, right? And then you have this. Well, of course, it's hard to draw in 3 dimensions, right? But then you know, so it looks something like this, and then you have your paraboloid somewhere here, right? So then you give data here, which is the physical data, and then somehow the trick is that you actually consider the whole section on the cylinder, which is an S3, right? So it's a 3-sphere, and then so you can somehow extend the data that you were given here to something that is the data on the whole of S3, right? And then once you do that, it's actually easy to prove. So you evolve so the physical data together with the extended data, and then so you evolve somehow the whole section with S3, right? And then you can argue that whatever you put here to extend the data actually doesn't affect the physical region because it's causally disconnected, right? So I guess so then you are in, and then you see that in fact the metrics that you are obtaining or the solution to the Einstein field equation is completely regular everywhere, right? And the only way you can actually see that there is a conformal boundary is because you have a conformal factor, right? So yes. So these are a particular example with this trick of extending beyond the conformal boundary is done, right? So then also there are some examples of numerics where they have done similar tricks. So they actually solve the conformal field equations, right, on sections which are S3, and then you only restrict the part that is inside the conformal boundary, right? So. Yes, right, but okay, so this is a good point, right? But then when you solve from an hyperboloid, so right, so this is a key point, right? So when you solve from an hyperboloid, so you don't know whether you don't know whether this hyperboloid is actually related to Cauchy data, right? So in fact this is an open question, right? So given some hyperboloidal data, how do you know where there's some initial data that has, right? And then so basically you are working on a space-time which didn't have this singularity, right? So you somehow you ignore everything that happened to the past. Okay. Yeah, but this is actually a good question. It's a somehow technical point there. All right. All right. Yeah. So somehow I guess the reason for looking at this hyperboloidal problem is precisely that. So you know that spatial infinity is complicated. So let's see how much you can go without actually trying to avoid spatial infinity, right? Okay. All right. So okay. So I guess let you say one thing that this somehow should be said, right? So the result is semi-global, right? Precisely because you cannot discover the whole of space-time toward the past from this data. So only somehow is between somehow contained between these dotted green lines. So you cannot reconstruct this, right? Unless you give information here. All right. So the first global result, right, from Cauchy data is the theorem by Pisodul and Kleinerman from 1990. So when they proved the nonlinear stability of Minkowski spacetime, right? So then they gave Cauchy data. And this, of course, this is done with a somehow completely different method to those used by Helmut Friedrich. So they're using vector field methods and constructing estimates, right? So somehow Helmut Friedrich's proof is very high level, right? It really uses very basic properties of PDE, something like Cauchy stability. But here, really, you have to look very carefully at the estimate, right? And then, so what they see is you give the data. If the data is close enough to data for Minkowski, then they have a global spacetime which is geodesically complete, and it has a global structure similar to that of Minkowski. However, they cannot recover the peeling behavior on Scry, right? And then for a long time, so this was a question, right, of discussion where it was some technical thing that the estimates were not good enough, and then but then if they work with more care, they should be able to recover peeling, right? But now it's understood that there is something fundamental going on here. So anyway, so whether you can construct spacetimes with a smooth null infinity, so was answered in the positive using some tricks, right? And this was done by Piotr Kruszel, so almost 20 years ago. And the idea is the following. So there are these gluing methods that are used to construct solutions to the constraint equations in relativity. And I will say a bit more about these gluing methods later on, right? But then the key idea is that you are giving me some arbitrary Cauchy data, asymptotically flat data for the antifield equations. So the theorem tells you that actually you can glue this data, so you can remove the asymptotic region of that data and replace it with say, the asymptotic region of Schwarzschild, right? With a certain mass, well, this is obtained through a gluing process, and then so you will have your arbitrary data in some compact set. There will be a transition region, right, where the constraints are satisfied, but you don't know exactly which solution you have. And then there is an exterior region where you know that the data is exactly Schwarzschild data. Right, and then for this space-time, you can actually show that the scribe will be smooth in the sense of Penrose. And why is this? So the idea is that, well, in the region, the asymptotic region where you have Schwarzschild, so we know that Schwarzschild, we understand Schwarzschild completely in this region, so we know that that means a nice smooth conformal extension, right? And then, so what you do is you can consider an hyperboloid somehow, like the one I have drawn here, so which starts on close to the compact region where you have the data, the arbitrary data, and then this takes off, so to speak, inside the rectangle, and then crosses, intersects Cry on this in the region where you have Schwarzschild, right? So this is an hyperboloid which is completely controlled, and which has a nice behavior in asymptotics at Cry. And then for this hyperboloid, then you can prove global existence, or semi-global existence, right? So if the data is small, then you can resolve everything to the future of the data, right? So then you have this region here, but then you also have the complement what was missing, which is Schwarzschild. So then this is so this will be an example of a spacetime with smooth conformal compactification. Yes. So, right. No, so you don't know really the mass until the end of the gluing construction, right? So this is somehow one of the so there are some parameters which are fixed by the gluing process. So in the original result by Corvino Schoen, you really didn't have. If you wanted to put Schwarzschild here, you were, so there was some in fact, yes. So if you wanted to glue to Schwarzschild, then the mass, and there was another somehow trivial parameter which was the center of mass. So there's a translation there. This was fixed somehow by the procedure, right? So you give your data, you will say how big is your region that you want to consider, and then the size of the transition region and the mass is given to you back after somehow you solve some PDEs, right? So, but yeah, it may have changed now, right? So, but I wouldn't say. Yeah, I mean, I think now we have more high-powered versions of this theorem. Ali. Well, so there are also versions of this for care, right? And in fact, so okay, in fact, so there's a more theorem that tells you can put any exterior correspond to any stationary solution you want, right? So yeah, so I think that there is some room probably to play around with the multipoles, right? Because if you want to put care, so you are saying that the multipoles have to be of the solution have to be of a certain form, right? So yeah, right. So yeah, so this would also and in fact you can also prove that for any stationary spacetime or stationary data, you will also have like a nice corner of spacetime where which is everything is smooth, as smooth as you want. Yes. No, I think you would be able to construct a BMS frame on the whole of this, right? So of course, there is some, I mean, if you have like a LIGO or one of the detectors right here, so suddenly everything is quiet, and then you will have some jump here, right? So there is some sort of, well, not discontinuous behavior, right? But there is some transition region here, right? So, and Okay, I see. Oh, okay, so thanks. Okay. Okay, so somehow this is slowly leading to somehow the main tool of and point of this talk. So somehow, so Helmut Friedrich was, so I guess somehow unhappy with this because his construction is somehow contrived, right? So there is some, it's a bit artificial, right? But somehow shows you that actually you can show that this space-time exists. But then you would like to ask or answer whether how is it the only way you can do this, or there are other ways of somehow understanding the structure around spatial infinity, which other than just putting everything to be time independent, right? And then so for this he constructed some initial value problems. So he has this set of equations called the conformal field equations, which I don't want to show here because they are very big. So, but I guess the gist of these equations is that they are a conformal representation of the Einstein equations. This means that if you have a solution to these equations, then whenever the conformal factor is non-zero, you actually get a solution to the Einstein field equations, right? So then, the point is that then you can use these equations to formulate initial value problems in the conformal picture, in the conformal space-time. This equation, and then at least in the case of spatial infinity, so there is a way of arranging things so that the equations and the data, despite the singularity that you have here, so you can somehow tamper things to get equations and data which are regular. So you somehow rescale the singularity if you want, and then this somehow gives you a setting where you can study this from the partial differential equations point of view. So how this looks like? Well, so somehow you start with standard picture, right, of spatial infinity, right? That somehow from Penrose's standard point of view, you have a point, and then somehow this point is blown up first to a two-sphere, and then you take into account boosts, and then this generates a cylinder. So this is also very similar to what Ashtekar and Romano did in the 70s, right? In fact, this work by Ashtekar and Romano really predates the work by Friedrich, like for more than at least 20 years, right? And then somehow, so what is interesting is so then this I0 really transforms to this cylinder. So this is not a conformal picture, but more like a sort of coordinate picture. So it's highly distorted, and then in this drawing, so then spatial infinity, the cylinder, meets null infinity, which is this horizontal hypersurface, and it meets in these sets in lila, right, which are called the critical sets, right? And so if you want, you can think of this as the endpoint of a future null infinity, and then will be also for past null infinity, right? And then somehow the idea is that you give some initial data on some hypersurface, and then you would like to study the PD problem around this about this boundary, right? So they are. So, but a key point about this object is that it is called a total characteristic. This means that actually all the evolution equations, conformal evolution equations, actually reduce to transport equations on this cylinder, right? So this means that you actually can transport information from your initial hypersurface to the endpoints of the cylinder, right? So this means that this gives you actually a way of relating properties of initial data with properties on stride. Okay. Yes. Right. No, it doesn't appear here because somehow the analysis by Helmut Friedrich actually assumes that the data is completely regular. right? So he only considers data considers data without logarithms. No, so that's true, right? So but it's an intentional, assumption, right? Because somehow, so what I guess the point of view Helmut Friedrich was the following: he wanted to understand under the best of circumstances, so you take data which is as nice as possible, and then you want to see what happens with that data, right? Okay. Okay. No, you don't see this. No, so this is really, so that's true. So here is really set up to be as smooth as possible in terms of the data that you have. Yes. In the yes, toward the future. Yes. Yeah. No, so that and also this comes later on. That's why I will go to that. Yes. Okay, so this is just really just to point out, right, that because of the particular causal properties of this cylinder, right, so you can actually transport information from from intersection of initial surface along the cylinder to the future and to the past, right? So and then you can actually do this for somehow the jets of arbitrary orders if you have enough patience and computing resources, right? So you can take say, the components of the Val tensor and take a look at radial derivatives of those, all right, and see how these radial derivatives behave, right, when you evolve them along the cylinder. And then the idea is that in fact, right, so you could be able to recover a Taylor expansion out of these solution jets, right? So then, as I said, so these solution jets are completely determined from the data. Perfect, right? And then here it also plays a role that you want the data to be smooth, right? So because you want actually to evaluate the data for these jets. Okay. Right, so somehow the idea, so this actually, yeah, so I'm engrossing very quite quickly on this, right? But this is really somehow the key point from, I think, or input from this approach is that because you can study the regularity somehow of the solution jets, modulo computational complexity, so that you can use in particular computer algebra to do this. And then you actually find that the solutions, right, they actually contain logarithmic divergences at these critical points, right? So at the level of jets, right? And then you have logarithmic singularities here and here, just at the level of jets, right? But then, because you have somehow control on the data, then you actually can play around and see which part of the data you have to switch off to remove some certain logs, and then you can do this as much as you want. Okay. And well, so doing this actually allows you to somehow to understand how properties of the data somehow relate, have influence on peeling. So here I have a theorem that I worked out some years ago with a former student of mine, and so you have some data which is is as nice as you want, and so this data, so in particular you want this data to be smooth, and then so we assume near to spatial infinity is that your initial data has a smooth point compactification. And then in this smooth point compactification, you choose some gauge, so conformal gauge, which has the property that in fact your initial metric is flat to corrections of order 3, right? So you can choose a conformal scale where in fact somehow the curvature vanishes at the point of spatial infinity, right? So then here, if somehow if there is a solution to the evolution equations, right, for this data, then this is somehow the assumption. If you have a solution, then from these jets that I showed, you actually can read off what would be the peeling behavior or non-peeling behavior of this solution, right? So then here I have a theorem, so where you so say like the more general case, then so you have peeling behavior for the radiation field and psi 3, but then for the other components you have this polyhomogeneous behavior, right? And then moreover, if you start making some extra conditions on the data, for example, you require the Cotton tensor of the 3 metric, right, which measure the deviation from conformal flatness. You require the Cotton tensor just to vanish spatial infinity, so only at a point. Then you recover one, you remove one of the logs, and then you can go, and then you can start requiring that some other derivatives of trace-free derivatives of the Cotton tensor vanish. Then you remove another log, and then if you require these conditions here again, so you take the derivative of Cotton, take trace-free part, then you take second derivative, and then you take the trace-free part of this, and you require this tensor to vanish at this point. So these are actually conformally invariant conditions. So then you can recover classical peeling, right? So I think I found this result very, very, very nice. So what I wanted to show them to you, because it really shows how you can actually control asymptotic behavior in terms of properties of the data. However, so there is a caveat here, which I stress this, is that you are assuming that actually that these jets give rise to a solution, right? And then this is somehow the missing theorem that we have, right? So we are assuming, so we're constructing certain asymptotic expansions, put in other words, which don't know whether it actually corresponds to actual solution to the Einstein equation, right? And yeah, so somehow this is the technical point that one would like eventually to solve. Yes. No, I is really a point, right? So you have the data. Yeah, it's really, so you have your initial, it's at this point, right? Which is, it really is a data, right? So you have on this hypersurface, you have a 3 metric H. There's a Cotton tensor of the 3 metric. That's right. Yes, of the initial, of the initial metric, right? So your metric is flat here to order 3, right? So in fact, so you start only seeing the Cotton tensor is really hidden, I suppose, here, right? In the old 3, right? So, yes. Yes. It's a sufficient condition, yeah. With yes, with my caveat, yes, that's right. Yes. Right. No, so in fact, well, so you are only solving the Einstein equation on this cylinder, right? So to obtain this expansion, right? Well, so you need to control the solutions, so look at the full equations outside the bulk, right? But then there are some technical problems with so you have a symmetrical parabolic system, but there are some degeneracies on the equations. It means that like you cannot really apply PD theory directly to those equations in the form they are, right? So the point is that on the cylinder is simpler because you remove from one radial dependence, and then you can decompose in harmonics, and then you can analyze everything really at the end in terms of ODEs, right? So I think this is somehow the key point. Okay, so I guess so. You wanted to bring your attention here that so there has been some recent work by Peter Hinz and Angas Bashi, where they also reproved the global nonlinear stability of Minkowski space-time. And then so they keep, so the new thing here is that they show the solutions will have the polyhomogeneous expansion. So somehow it seems that they were so basically proving the sort of thing that one would like to have in this context. Right? So there are logarithms in the expansion. And I think this is actually a very important result, right? And I think really said somehow where I guess the field should be moving, say, in mathematical relativity. You want to fill in somehow some of the gaps that I'm showing here. And I guess just to add that, well, the conclusions from the analysis at spatial infinity are generic. So many of these things really arose, I think, in first instance in analysis of stability of solutions, right, of, say, the Minkowski space-time. But in fact, many of these things are completely generic, right, because somehow the properties of spatial infinity are independent, or the generic properties are independent whether you are working with Minkowski or perturbations of Minkowski or you have a black hole, right? It's somehow a localized problem near infinity. And then I guess the other selling point is that, well, so with this setup of Friedrich, you can actually compute asymptotic charges and other observables and the relation to initial data. Okay, so then I see I'm actually particularly slow today, right? But so I really wanted to discuss the last part, which is somehow how you can use this thing to compute BMS charges at spatial infinity. So this is work with Mariem Magdy, so former PhD student, and Kartik Prabhu. And okay, so I guess what we want to look at the BMS charges in this setting. So I will not say very much about this because everybody I think here knows what those charges are and why we care. We also have seen this before, right? So then I can safely skip these things. And then so in this particular study, because so we concentrated on supertranslations, right? So the parameterization of codes of scribe, right? So which are generated by adding a smooth function, right, to the boundary coordinate retarded time on scribe. And so okay, so there is somehow a technical aspect here which I should also indicate, right? Well, usually when you talk about these things, right? So charges or many of the things in asymptotics, this is done in some adapted frame which is adapted to the geometry of null infinity, right? So somehow for, I guess, historical reasons, I belong to the tradition that likes to use like a Newman-Penrose formalism, but then I know that in this community, people like boundary coordinates, right, more. But anyway, so this is something that has to be, I have to mention this because somehow everything that we're discussing about this Friedrich's cylinder is actually done in another gauge, right? And then so there is a non-trivial aspect that when you want to write things in one terms of the other, you have to compute the coordinate transformation, right? So this means that you really have to look very carefully at the prescription of how the gauge is prescribed. And yeah, so there are certain conditions here to this, which I probably, well, so just to say that, well, of course, you are working with something they call the Newman-Penrose gauge. So there is some sort of a choice of coordinates, which are basically boundary coordinates, but then you also use a frame, which is somehow adapted to null infinity. And then there is also, if you are in the conformal setting, there is some conformal freedom that can be used to eliminate certain components of the connection and then certain components of the Ricci curvature. I just mentioned this, right? So you have, so I guess for this sort of calculation, I guess takeaway message is that you have to know very well how your Newman-Penrose frame is defined, how the Friedrich gauge is defined, right? And then translate between each other, right? And then there is a general, I think, algorithm that was worked out some time ago by Helmut and postdoc at the time, so Janusz Kanner. And okay, so what we would like to do is, so we have these the BMS charges, right? And then so I'm taking this formula for the immediate charges given in a paper by Kartik Prabhu, right, which involves somehow the component, the Coulomb component of the Val tensor, also involves the shear tensor on scribe, right? And then then you're integrating this object respect to an arbitrary function on the sphere. So particularly you can think of this lambda to be one given harmonic, so for a particular choice of L and M, right? And it will give you your charge. Okay, so basically, our task is to take this expression, right? Rewrite it in the Friedrich gauge, right? And then what we want to do is evaluating some cut, and then basically take this cut down to the endpoint of future null infinity. Right? So this is somehow our main task, right? So you start some cut here, and then, well, in fact, you will be closer, and then you want to evaluate this expression at I0, and then compare with the counterpart on the same construction on past null infinity. And then so this of course leads you to try to address some questions. So under which conditions are these limits well defined? And then of course whether the charges that you compute are basically the same. So of course we are not by no means the first ones to look at this, right? So Strominger, Mariem, Kartik Prabhu have looked at this, and many other people which I'm probably forgetting here. Right? And I guess somehow a selling point from this is so somehow the idea here is that when we take the limit, what we want to do is we want to rewrite this using this transport equation on the cylinder. We want to rewrite these charges in terms of quantities that can be read off from the initial data, right? And then so you do that for the future, and then you look at for the past, right? And then because so these are related to certain parts of the data, so you can compare whether these parts are the same, and then if somehow they are coming from the same part of the data, we'll say that you actually can you can identify the charges. And I guess because we are based or making use of the Cauchy problem, so we have to look at a particular choice of initial data. And fortunately, there was already a theorem for us to do this by Lan Huang. And basically, so using gluing techniques again, so she can show that that there exists generic initial data for the Einstein vacuum field equation. We have this asymptotic behavior, right? So you have the usual like mass aspect here, where the A is a constant, and then you have at the same order a correction or an extra term, which depends on a function on the sphere, right? And then has arbitrary number of multipoles. And then also for the intrinsic curvature, so you have the same thing. So the leading term contains some arbitrary function on the sphere. So then basically, so we do our all. So we actually, what we do is take this data, and when we transport this the information from this data along this cylinder. Okay, so this is the idea. Again, just repeat. So you will have Lan Huang's data here, and then you want to evolve this, and in particular, you want to evolve the quantities that appear in the formula for the charges, and you want to transport them along to the future and to the past. Okay, and then so basically, so what happens is the following, right? So in the formula, yes. So I will then thank you. So I will then, well, so basically, as I said, so you can reduce the problem to looking at certain ODEs, right? So they are basically Legendre equations for which you have a part which is regular and a part which is singular when the singularity is a logarithm, right? So this is somehow the trick here. So and then you can also compute the other part that appear in the BMS chart. In particular, you can look at this shear tensor, and then so remarkably, this shear tensor actually goes to 0, really at these critical sets. And I guess that then what, just to conclude, really, so what the key point is that you have to impose certain regularities to be able to evaluate the limits. And then regular solutions are obtained if the odd parameter harmonics in this function alpha, right, that goes with the mass aspect, if they vanish, right? So this means that in particular, so only BMS-supertranslation charges with a L even parity have a non-trivial information, right? So this is the key somehow outcome from this calculation, right? So in the linear case, it is somehow different, right? And this has to do with the fact that constraints in full G are different from the linearized case. In this case, there are non-trivial charges for even for I should have said odd, for odd parity, the odd parity case of the typo here. Okay, so you get charges, but here in this case somehow this regularity condition actually kills off one of the charges, right? And then so from that, I guess so when this, and then from that, in the cases where these charges are well defined, then these charges are actually are basically the multipolar structure of this quantity alpha, right, on your data, and then you can identify these charges at the two on future and the past, right? And I guess so. The nice thing about this is that you are not really requiring any antipodal matching assumption for this. Right, so it's really sort of putting conditions on the initial data, and probably I will stop here. Then, well, I will still around here. If you have any other questions, happy to discuss that. So thank you very much.